today's video, we're going to look at how we can track an object that has been launched vertically from where it started on the ground to where it's going to end on the ground. Now, we're not looking at objects shot out at an angle. We're just going to look at an object that's fired straight upwards in this video. So, let's take a look at the problem and begin setting it up. A baseball is thrown vertically in the air with a velocity of 45 meters per second. That's not a question, that's what's going on. How long will it take to hit the ground? What is the baseball's apogee? Okay, so first thing we're going to do is list our variables. What do we know? We have acceleration time, initial velocity, final velocity, starting position, and ending position. These are going to be haunting you in your sleep because we've gone over them so much. The initial velocity is 45 meters per second. That's the velocity at which we launch the projectile, and we'll call that the starting velocity. We know that the acceleration due to gravity is negative 9.8 meters per second, and the negative is indicating a downward vector versus the initial velocity, which has an upwards vector, which is why we left it positive. We also can say that our initial position is 0 meters. Now, what else can we figure out from this problem? I don't honestly see a whole lot, which leaves us with a lot of question marks. One of the questions that's being asked is how long will it take to hit the ground? Well, that's a question mark. Another question is asking what is the baseball's apogee? That's the final position at its highest point. That's a question mark as well. And I guess we can assume that final velocity is a question mark, although I don't see that it's being asked for in the question, so I might get rid of that and just cross out final velocity. So we've never dealt with problems before that have two questions, basically, or two things that we don't know and we need to solve for. And so we're going to be left with, I guess, what are we going to do with this? So I'm going to go ahead and think about the problem like I would normally any other problem. I know that I need to know time, and I know that I need to know final position, and most importantly, I know that the final velocity is unknown, and it's not going to help me in this problem, so I should just try to find an equation that doesn't use final velocity. So I'm going to look for equations that don't have final velocity in them, and that's going to be this one, that one. Let's see, that one has final velocity, can't use it, and this guy has final velocity, which means I can't use it. So it seems like I'm stuck with using this equation. So the problem with using this equation, though, is that I need to know time, and I don't know times. So what can I do in this case? Well, I'm going to go ahead and decide that I'm going to plug in various times and see what data I can get. And I'm not only just going to plug in various times, I'm going to plug in times that will allow me to track the position of this projectile as it's working through the air. So this is going to involve constructing a graph and a displacement versus time graph. Now, in this displacement versus time graph, I know one point already, which is 0 seconds, 0 meters. I haven't launched it yet, and no time has gone by, which means it hasn't traveled anywhere. Alright, so now I'm going to go ahead and use this equation, and I'm just going to plug in a time and see what I get. And the most likely time I should probably plug in is 1 second. So what happens after 1 second's worth of travel? Alright, so here's my equation. Final position, and we're doing that for 1 second. So final position equals, let's see, initial position, which is 0 meters, okay, plus the initial velocity, which is 45 meters per second, multiplied with time. And I'm going to say time is 1 second right now. And I'm going to add 1/2. Pause here for a second. I'm going to add 1/2 multiplied with the acceleration due to gravity, which is negative 9.8 meters per second every second. I'll leave off the units because I don't have room. And then it's time squared, which is 1 second squared. All right, so my final position is going to be equal to, and I can cross out the initial position because it's 0. Okay, 45 meters per second times 1 second is just 45 meters, and the seconds cancel out, plus 1/2 negative 9.8. And you know what? To make my math a little bit easier, instead of saying negative 9.8, I'm going to say negative 10. That will make my math just a little bit easier. Meters per second every second. And 1 second squared is just 1 and second squared. All right, so XF equals 45 meters. And I'm going to multiply half with negative 10. That gives me negative 5 meters per second every second. Oops, let's ignore that. And that's going to be multiplied with 1 second squared. So what I'm doing here is just showing my work all the way through this problem. All right, notice the seconds squared are going to cancel out the 2 seconds here, and that's going to leave me with just meters. So XF equals 45 meters plus negative 5 times 1, which is just negative 5 meters. And that equals positive 40 meters. All right, so in 1 second's worth of travel, this projectile is going to travel 40 meters in that 1 second. I'm going to add that to my data table. All right, let's take a look at 2 seconds and see what happens in the second. All right, so here's all my information. I'm going to speed through this because we should be able to set it up. Now, instead of 1 second, I'm now looking at what happens with time being 2 seconds. So I'm plugging 2 seconds into this. And again, I can ignore the initial position. And when I multiply 45 meters times 2 seconds, I get 90 meters, and the seconds have canceled out there. And all right, plus 1/2, and I'm going to estimate this to be 10 meters per second every second, times 4, because 2 squared is 4, and s squared is, well, second squared. So XF equals 90 meters. 1/2 times negative 10 is negative 5 meters per second every second, times 4 seconds squared. And the seconds again cancel out, leaving me just with meters. So XF equals 90 meters plus negative 20 meters, because negative 5 times 4 is negative 20 meters. And that gives me positive 70 meters. All right, this is looking pretty good, because I'm seeing that in 2 seconds, it's risen up to 70 meters upwards. All right, so this seems to indicate that the projectile is leaving my cannon and traveling further and further away into the sky. All right, so I'm not going to go through all of the math again, so I'm just going to set up each problem, because now we're going to look at what if we want to check 3 seconds. Okay, and with 3 seconds, we find that XF is equal to 90 meters. All right, that's looking pretty good. If we look at XF equals 4 seconds, then we're going to find that, here's all my information, we can find that XF is going to equal 100 meters. All right, that's nice. All right, so you might be noticing something, we'll get to it in a second, but you might be noticing that the distance that it's traveling each second is slowly going down, down, downs. And we'll take a look at that in a second. But let's see, so 3 seconds, 90 meters, 4 seconds, it's gone 100 meters. Yeah, so check it out. Between the first second, it went 40 meters. In the second, it only went 30 meters, from 40 to 70. Between 2 and 3 seconds, it only went 20 meters further. And then between 3 and 4 seconds, it only went 10 meters further. So it seems to be slowing down because we're getting less distance per second. Let's check out the 5th second and see what we get. So plug in 5 seconds into our equation, and we find that 5 seconds leads to a displacement of 100 meters. All right, so 5 seconds equals 100 meters. All right, so what is this an indication of? Notice that the distance didn't change between 4 seconds and 5 seconds. This is an indication then that we have reached apogee with our projectile. All right, cool. So one of the questions was, what is the baseball's apogee? We'll take a look at that on our graph in a second because we're going to graph this data as well. All right. Now, the other question is, how long will it take to hit the ground? So I'm going to keep going with my data because notice that the projectile hasn't hit the ground yet. So I'm going to get rid of that and plug in 6 seconds and see what happens. All right, so 6 seconds. And what's going to happen? XF is going to equal 90 meters. All right, so that's important because 6 seconds, 90 meters, this is an indication that our projectile is now heading back downwards. So my projectile was 40 meters from me, then 70, then 90, then 100, and then it stayed at 100, and now it's only 90 meters away from me, and it seems to be coming back closer to where it originally got shot out from. Now, if you want, you guys can go ahead and solve for 7 seconds, 8 seconds, 9 seconds, and you can pause this and do that, or we can just take a look at the data and move on. So let's go ahead and take a look at the data. All right, so let's graph what's going on with this data because I think it's important no matter what to have a visual for our data tables. So let's see what's going on. So 0 seconds, 0 meters. 1 second, 40 meters. 2 seconds, 70 meters. 3 seconds, 90 meters. 4 seconds, 100 meters. 5 seconds, 100 meters. 6 seconds, 90 meters. 7 seconds, 70 meters. 8 seconds, 40 meters, and 9 seconds, 0 meters. All right, awesome. So you guys are going to notice, if you follow my arrow here, we have this beautiful sloping line, it looks like, and this is a clear indication on a position versus time graph or a displacement versus time graph that we have deceleration. Now, the object reaches apogee somewhere up in here, and then it begins accelerating back down to the ground because notice the distances each second become greater and greater and greater. Awesome. So we see a beautiful graph here of deceleration, reaching apogee, and then accelerating to the ground. So let's just put a line to this, make my dots a little bit bigger. All right. And looks something like that. Awesome. So what can we say in answer to these two questions? So first of all, we can say this. It is going to take about 9 seconds to hit the ground. We can say that pretty assuredly. That's what our math is telling us. We can see that on the graph as well. So it will take about 9 seconds to hit the ground. What else can we say? Well, to answer the other question about apogee, we can say that apogee is going to be slightly greater than 100 meters. And we are saying slightly greater than 100 meters because, if you follow my arrow, notice that the curve goes above that 100-meter mark, so we know it's going to be slightly greater than that 100 meters, all right? Otherwise, it would look really weird if we made a flat line between 4 and 5 seconds, so it's slightly above that. All right. So looking at this problem, what we've done is we've taken the fact that we had two missing variables that seem to be pretty important, two question marks, and instead of trying to solve exactly for each of those, what we did was we just plugged in a variety of times and just tracked what's going to happen to this projectile as it travels through the air. And by doing that, we can get a pretty clear picture as to what's going on with this projectile every second of movement. Where is it going to be? Now, you may not know this, and you will learn this in Algebra 1 pretty soon, but what you're looking at here is a parabola. And a parabola as a line graph is a clear indication that you're looking at a quadratic equation. And a quadratic equation is the equation that we use to solve this problem. So if you look back towards the beginning of your notes, we use an equation that had t squared in it, and then a t, and then being added to something that didn't have a t. And that's an indication that that's a quadratic equation. And those of you guys working in Algebra 1 right now are factoring some quadratic equations. So if we graphed any of these quadratic equations, even the ones you guys are working on in algebra, this is what it would look like. Either a parabola that has more of a rainbow look, or maybe a parabola that's flipped upside down and has like a deep valley to it. So this one looks more like a mountain. We have parabolas that have kind of a valley look to them as well. All right, so one other interesting point before we end this video: what would happen if we kept going with our time? For instance, what if we put in 10 seconds? What we would find is that the math is going to keep going. So at some point, humans have to stop and say, okay, what's reality? Because the math is just totally theoretically based, and it's just going to keep going and going. So at 10 seconds, according to the equation, the projectile is going to be at negative 40 meters. Now, what does that mean? That means that the projectile has hit the ground and is now burrowing through the ground negative 40 meters below us, and it's just continuing to go. Now, that doesn't make a lot of sense, so what we want to do is probably just stop right where we see it hits the ground, maybe do one more point after that, but likelihood is that projectile is not burying itself deeper and deeper and deeper into the ground. That would be pretty insane. All right, so we'll practice this in the next few days, probably leading up to Thanksgiving break. And again, think about how this affects what you guys are thinking about with your cannons and the experiments that you'll eventually set up using your cannons.